How could math help you any more than with your finances? That's what we're going to be talking about for the next couple of weeks. Let's look at the basics first. Interest. This is free money that you can get. Remember what interest is? And we're going to start with simple interest. Simple interest is an amount that you get, that you accrue in an interest-bearing account over time for a single deposit. In other words, your grandmother gave you $100 once and you put it in the bank. Not a bunch of payments, just one single deposit. We'll start with that now. And you get interest compounding once a year. Hence the term simple. A single deposit, once a year's worth of interest. Now, we're going to have a formula for simple interest. It's P times R times T. P is the original amount that you put in, the principal we call it. Okay? R is the rate of interest, which is usually some percentage, so get used to that being a decimal. And of course T is the time that you invest this money, the time that you let the bank hold it. And that's usually going to be in years.
Allow me to demonstrate.
Okay, let's look at a typical problem. We want to know the interest that we would make on $2,000 for 1 year at the rate of 7% simple interest. Now, they said simple interest in this problem, so that's just per year. So we're going to take the principal, 2,000, multiply by 7%, and multiply by the time, in this case 1 year. Now that 7% is a decimal, 0.07, 7/100ths, remember. We do the calculation, and we get $140. Now that's interest.
It's mine, you understand? Mine, all mine.
Of course, you get your original 2,000 back also, so you really end up with 2,000 and 140. So we're going to come up with a new word here, how much we've accrued after 1 year for 2,000 at 7% simple interest. Similar problem, but we don't want to account for just the interest. We want our principal and our interest because that's how much money you get back. So we have a new formula. We have our original amount, 2,000, plus 2,000 times the interest rate. So hopefully you can see how I come up with a formula here of 2,000. I don't want to write 2,000 twice. It's going to be 2,000 times 1, the original amount, plus the interest rate. So you're going to be seeing this 1 throughout the whole rest of the class because you get your original money back. Well, you're going to see 1.0 whatever the interest rate is. Okay, so get used to seeing that 1 because you get your original money back. And that, of course, would be the amount you would get.
Are you pondering what I'm pondering?
Well, what if we keep it in there longer? We're starting to make a little bit of money. How much would we accrue after 2 years for the same amount of money, $2,000? We're not putting any more in. We're just going to start with $2,000 at same interest rate, 7%. Well, we're going to get the first year, we're going to get our $2,000 times 1.07. Then we're going to take that amount after 1 year, and we get another 7% on that. So I'm going to multiply that by 1 because I get the original amount back, and 0.07. So that's what we get for the second year. Get a little bit more money, don't we? $2,289.80. Well, let's see if we can come up with some sort of a pattern here.
Show me the money!
What would be accrued after 3 years? Let's look at it. Well, we'll have our 2,000 times 1.07. Of course, that's the first year. And then we'd multiply times 1.07 for the second year. And then what are we going to do for the third year? Of course, we're going to multiply by 1.07 for the third year.
Excellent.
Get even more money, right?
Pay attention, son. Look at me when I'm talking.
Well, so our general formula to calculate amount accrued with using just simple interest is going to be A being accrued That's how much you get at the end. P being principal, R being rate of interest, and T being the time in years that you invested it, is, I hope you appreciate, principal times 1 plus the interest rate to the T. We're going to multiply by 1 plus the interest rate times itself that many years, as you saw in the last example. That's the key.
It's not the principle of the thing, it's the money.
Let's try and use this formula for a different problem, because we usually don't keep money for 1 or 2 years. You keep it for 5, maybe 10 when you invest money, until your children get to college or something like that. So it may be for a long period of time. This formula is going to become much more useful. Well, in this case, we're going to invest $500 at a rate of 4.5%, and we're going to see how much we have after 5 years. So we'll multiply 500 times 1 plus, remember what 4.5% is, 0.045, and then we'll multiply that portion to the 5th power. Well, this is a job for your calculator, and let's do that. Go ahead and take the time, multiply 500 times, make sure you use your parentheses, 1 plus 0.045 and parentheses, use your to the button, to the 5th, and I'm hoping you get, wow, $623. That's basically $123.09 of free money, isn't it, over 5 years. Now, that's simple interest. That's if they compound the interest 1 time a year. But you know what? Banks really compound more often. That's good news for you. They more often than once a year, don't they? Of course, if we put in, let's put an easy number, $1,000 at 8% simple interest, that's compounding once a year, we'd get, as we remember, our original amount, $1,000 plus 1,000 times the 8%, or 1,000 times 1 plus 8%. Get the idea? And we get 1,080. That's simple interest. That's compounding once a year.
How about a little fire, Scarecrow?
What if we compounded twice a year? I hope you expect you're going to get more money. Well, let's see. How much are we going to have after 6 months? Well, I'm going to have my original amount, 1,000, plus 1,000 times, you don't get the full 8%, you get half of that, don't you? Because it's only been 6 months. So, or we could say 1,000 times 1 plus half of 8%.
Is that your final answer?
Well, wait a minute. We want to do it for the whole year. So after 12 months, and that'll be after 6 months, after 12 months, we'll take that amount, same amount, and then we have to multiply it again by 1 plus the interest rate divided by 2. Why divided by 2? Because we compounded twice a year. Well, guess that's $1,081.60. It's not that much more, but it is more. It's about $1.60 more. Just compounding twice a year as opposed to once a year, which is simple interest.
Now you listen to me. I want details, and I want them right now.
Okay, we're not going to belabor this. We're going to get right to the formula for multiple compounding. Sometimes, certainly, they compound more than twice a year. They compound 4 times a year, maybe once a month. That's often. That would be 12 times a year, of course. So,
It's mine, you understand? Mine.
the formula for multiple compounding of the accrued amount is going to be principal times 1 plus your interest rate divided by that M we're going to put in there. And M is the number of periods or number of times per year that it gets compounded. In the last problem it was 2, wasn't it? And we're going to take that and we're going to raise it to the MT power. And last time it was to the 2T power, right? Because M was 2. So you're going to actually use that M twice.
Now what am I gonna do?
Let's try one. How much would an investor accrue if they took $500 at an interest rate of 7% for 4 years, and the interest is compounded monthly. Okay, monthly means, of course, 12 times a year. Well, let's put in all the magic numbers, and you see where you get your 500 for principal, 7% for interest rate, the 12 is the monthly, and T is 4 years in this case. Okay, we'll use your calculator. But I gotta warn you, this is what we're going to put in. Note the orange parentheses. If you don't put those parentheses there, it won't work. It's critical that you put parentheses around any exponent, because the order of operations, if you didn't put them, would have it raise all this to the 12th power, get an answer, and then multiply the answer by 4. That's not what we want. We want to raise everything to the what? To the 48th power, to the 12th times 4th power. So we need it to do that first. So any exponent, make sure you put parentheses around it. And look what we get here. The answer should be $661.03, approximately. Let's do another one. How much would an investor accrue investing $3,000, this is a one-shot deal, at an interest rate of 10% for 5 years, when this time we're going to be compounded quarterly? That's another common one. Things are compounded quarterly. Of course, the magic number there is 4. We put all our magic numbers in. 3,000 for the principal, 0.10 for the interest rate, and 4 for the M, and 5 for the time. Get out your calculator. Get busy. And you should type in, don't forget your parentheses. Always put parentheses around an exponent if there's some calculation to be done. And the answer you should get is $4,915.85. Not too shabby for free money. Now, believe it or not, we're going to have to get a little bit more advanced in the mathematics if we're going to actually simulate exactly what banks do. And that's going to involve logarithms. And I think usually we need a review. So let's talk a little bit about what we should know before we start using logarithms. Consider this exponential equation. Okay? Y equals b to the x power. I'm going to flip it around. If y equals b to the x, then b to the x equals y. What does that have to do with logarithms? Well, I'm going to change the representations of these, okay, so that I can remember them.
Do you mind telling me what this is all about, mister?
I'm going to say b to the e equals n instead of b to the x equals y. Humor me. Just a second. The reason I wanted that to be a b is because I remember that it'll be the base. Okay, you knew that. Isn't that the base? And the reason I wanted that to be an e, of course, is that it's the exponent. And the n, what is that? Well, I call that the number, because it really is a number, isn't it? It's just a number sitting by itself. Okay, consider this equation, if you would.
If you don't start making more sense, we're going to have to put you in a hole.
Well, the word logarithms really means, and I've got to get you to relax your mind, the word logarithms means the exact same as the word exponents. So what color is the logarithm in this picture? Of course, it's green, because the exponent is green. This could be read, the exponent, couldn't it? The exponent using a base of b to get n is e, because the exponent is e. Well, I just told you that exponents are logarithms, so I'm going to replace this verbiage with a fancy sentence. This means the same thing. The exponent using base b for n is e. Well, guess what? The logarithm using base b for n is e. Now, you're not used to seeing this, perhaps. I hope you've seen it before, but I want to warm you back up. Okay, so the logarithm, of course, we know the base is b for the number n, and you're not used to seeing the answer there, is it? The n is the answer. Some people like that to be an a. is e. You're certainly not used to seeing the exponent in that position, but this is the way we'll work with logarithms, because they are exponents. They're the same thing. Logarithms are exponents. Remember that above all. Okay? The logarithm equals the exponent. Now I call this the old switcheroo between these two forms of the equation. B to the e equals n means the same thing as the logarithm base b of n equals e. Once again, logarithms are exponents.
Darn tootin'.
Okay? Let's practice this old switcheroo,
What would you do with a brain if you had one?
and we'll get familiar with logarithms. Okay, 2 to the 4th, 2 times 2 times 2 times 2. We know that equals 16. How could we write this with the old switcheroo in logarithm language, if you would? Well, that means the exponent, or rather the logarithm, using a base of 2 to get 16 is 4. That's another way of writing this exponential equation. Let's work backwards. This would be, let's see, log base 5 of y equals x. Of course, the base is 5. Now, what's the exponent in this case? The logarithm equals the exponent. So this would be 5 to the x equals y, or y equals 5 to the x. Remember, the answer is not where you usually see it, is it? Well, we can use that to solve this equation. Let's see. Let's put it in. Let's use the old switcheroo and figure out what x is. Let's rewrite it in a different way. The base is 8, and the exponent in this case, remember, the logarithm equals the exponent. So we'd write 8 to the what power is 64. Well, now it's easier to solve, isn't it? 8 to the 8 to the 2, so x is 2. So always, you're going to have to be able to switch between these two if you're truly going to understand logarithms. Let's solve this one. Not a problem. That would be the base. I always say the base first. 5 to the, what's the power? What's the exponent? Well, the logarithm is equal to the exponent. So 5 to the 3 is what x equals. And what is 5 to the 3?
I'm dangerous. I'm very, very dangerous.
See, we can solve these equations if we switch between the two. You have to know how to switch them. Of course, you'll have to know what the base is, and you'll have to know what the exponent is, and the other one falls right into place usually. Now, since exponents are logarithms, and logarithms are exponents,
Excuse me, Professor Brainiac.
shouldn't logarithms follow the same rules as exponents?
You are correct, sir.
Well, it would behoove us, if they follow the same rules as exponents, to perhaps review just a little bit the rules of exponents, because they're the rules or properties of logarithms, since logarithms are exponents. Remember with exponents, when we multiplied two bases that had exponents, what did we do with the exponents? We added them. X to the a times x to the b equals x to the a plus b. That was a rule of exponents. Well, that's going to be a rule of logarithms. The logarithm of a times b, the exponent of a times b, the logarithm of a times b is the logarithm of a plus the logarithm of b. There's another since there's another property of exponents, and exponents are logarithms. Remember the property of exponents, x to the a divided by x to the b is x to the a minus b. Well, when we divide numbers with exponents, we end up subtracting the exponents. Since exponents are logarithms and logarithms are exponents, they'll follow the same rules. The logarithm of a divided by b, you can subtract the logs. The log of a minus the log of b. And those are pretty useful properties. But the most useful of all, I think, is the exponent of exponents. Remember x to the a to the b? What was the rule that you did there with exponents? Well, you multiplied them. So to exponentize exponents, the shortcut was to multiply them. Well, guess what? to exponentize, is that a word? To exponentize logarithms, logarithm of a to the b, we multiply. Of course, we multiply, we bring the b down in front. Okay, and you like it down in front. Much easier to handle down in front like that. This is going to be the most useful of all the properties of logarithms, as it was very useful as a property of exponents.
Pay attention, boys. I'll show you how it's done.
Let's review these properties by doing an expansion. I call this an expansion. Let's break this up into a bunch of them. This logarithm can be broken up into a bunch of little logarithms. Remember what division becomes. Division becomes subtraction. So that's going to be the log of a to the third b minus the log of c squared. Remember what multiplication becomes. Multiplication of logarithms becomes addition. Okay, and here comes the big useful one. Remember the rule of exponentiation of exponents, or should I say of logarithms, becomes multiplication. So you can bring them down in front when they're exponents. You could even break it up further, couldn't you? 3 log a. You could actually break a logarithm up into a bunch of pluses and minuses. And believe it or not, that's what your computer does. That's how it does calculations. It changes all exponents and multiplication and division into a bunch of additions and subtractions using a logarithm. So you don't need to know how to make your computer work. It'll do it for you, but it is something nice to appreciate.
Hey, this is great, man.
But now you know the rest of the story.
Now there's another thing
Insufficient
you're
data.
going to need to know about logarithms if we're going to use them on our calculator. This one looks like it doesn't have enough data, does it? It doesn't have the base. I need to know the base to know what, if I to pull the old switcharoo and raise that base to 1.3. Well, what you need to know is if they don't give you the base, just like in anything, if they don't give you the base, what base do we count in? We count in base 10. So if they don't tell you the base, it's called a common logarithm, and you have to infer that it's going to be a base of 10. Well, now that you know it's a base of 10, you can type into your calculator 10 to the 1.3. That's a crazy exponent, but 10 to the 1.3, and you can get the answer.
Transfer of data is complete.
Get the answer to this equation. It is about 20, 19.95. That doesn't surprise me because 10 to the 1th is 10, and 10 to the 2th is 100, so it should be between those two, and it is. Now you're going to need to know how to take a common logarithm using your calculator. A common logarithm. That's log. There's your button. Find it. Okay? And you'll have to use enter. Those are the only, you know enter already. So to take the log of a number, you would hit log, put in whatever the number is. Let's take the log of 19.95. The common logarithm of that, hit enter, and you get the answer. Okay? When I ask you to take a log, I mean, unless I tell you another base, I mean common log, and you can just use base 10 by hitting log on your calculator.
Missed it by that much.
And the last problem, it says about 1.3. So close enough.
Excuse me, Professor Brain.
Now what does this have to do, all this logarithm stuff, have to do with finances?
This is a pickle, George. This is a pickle.
Well, let's go back to our formula for multiple compounding. And let's look at a problem. How long would it take an investor to double an investment? We're going to get a problem like this. How long, where they're asking for time, would it take an investor to double an investment of $600 at an interest rate of 12% when the interest rate is compounded monthly? Now remember, we're looking for time. Let's look at our equation.
I'm back, baby!
Remember the equation, the general equation for compounding and multiple compounding. I put in my numbers. Now, I put in the 600 for principal. The 1200 came from because I want to double that, so I know what number I want. I want 1200 for accrued. I put in 12% 0.12 for the interest rate, and I also put in 12 for the M for how often I'm compounding. Okay, and the only thing I don't have is t. Now this is going to be a little bit of trouble because I've got to solve for t, and t is in the exponent position. Well, we'll start getting rid of things. I'm going to divide by 600. That'll get rid of that. But how am I going to get rid of... Oh, I can change that. I can change 0.12 divided by 12 to 0.01. That'll help. And I can add the 1 and the 0.01. But still, how am I going to solve this? Well,
Here's someone who can help you.
as long as you do the same thing to both sides in an equation, it's fair. And this is the big kicker. We're going to take the log of both sides. Why would I want to do that? Remember your rule of logarithms. If you take the log, where's another place I can put that 12t? Well, now you've got it. If you use that rule of logs, remember the rule of logs says you can take the exponent, the log of something to an exponent, and multiply by it. Bring it down in front. Well, now it's down in front. I can start taking things away using division. Okay? That goes away. I can find out what the log of 2 is. I can find out what the log of 1.01 is using my calculator. And then I only have one thing left to do to find t. Divide by 12. And I know what t is. How about that? So you can solve for an exponent if you use this logarithm trick. Whenever you can't get to something, you're going to have to take the logarithm of both sides. That'll move it down in front, and then you can kill it by division. Okay? Let's look at another one where we're solving for time. There it is. How long? Right away. Time. How long would it take an investor to earn $200 of interest with an investment of $1,500 at an interest rate of 10% when the interest rate is compounded semi-annually? That means twice a year. Okay? Well, get that old formula for multiple compounding and put in all your numbers. Now, the accrued number might be a little bit tricky. We want to accrue, remember, accrued is your original principal plus your interest. Okay, so we're not going to put a 200 there. We're going to put a 1,700. Accrued is original amount plus your interest. Okay? Okay, let's see. There's a little bit more to this problem than you may think you know. I'm going to divide by 1,500 to get rid of him. Okay? That'll go away. And I can divide those zeros out of there. Okay? Now, let's replace that with 1.05. That's what 1 plus 0.10 divided by 2 is, 1.05. Okay? Now, I'm not going to do any calculations just yet. I'll show you why in a second. I've got to get that 2t out of the exponent. Do you remember what the trick is? Take the log of both sides. Take the log of both sides. Whenever you're trying to get at an exponent, what does that buy you? Remember the same old rule with the logarithm of a number to an exponent allows you to take that exponent and put it down in front. Now it's easy to get, isn't it? I'm going to do both at once. I'm going to divide by 2, and I'm going to divide by the log of 1.05. And I have all that huge calculation, and that's what t equals. Now I got to tell you something. You see this calculation on the left? I strongly suggest that you do this as one big fat calculation on your calculator. Okay? Every time you hit enter on your calculator, it's going to round. So if you only do it as one calculation, you'll get a much more accurate answer. Okay, and with your money, you want it exact, right? So put all that into the calculator as one calculation and then hit enter, and I'm hoping you've got a pretty exact answer. The answer to this question should be 1.28 years. Okay, that's all for today. Oh, now come on, be nice. We'll see you next time. It's your turn to go do the homework. Remember your tricks using logarithms. Okayty? Aloha.